Yeah. All right. Here we go.
Okay, grand tour.
Sure. So this is the lab space we've got here in Worcester, Massachusetts. So yeah, we have right now we're doing some LK99 replications based on SCTL. They've been posting videos to YouTube, one of which demonstrates flux pinning, but there's some uncertainty with that. It's interesting nonetheless, so it merits some. It merits a further look. So these we're all just preparing various salts. We have different recipes besides the lead recipe, and as I mentioned in the other video, we actually did get some strongly paramagnetic particles.
And this is the LK99, right?
Yeah, these particles are the LK99 recipe that the article claimed, except half of the oxygen on the oxide has been replaced with sulfur. So
okay.
It's half sulfide. And so we thought that might be an interesting thing. And then also one of the things we want to do is to dope it with excess phosphorus and make it in a reducing environment, so maybe a little excess copper and lead to keep it all in the right oxidation state.
Okay.
So and the other thing we tried with this that seems to be kind of the secret sauce for this is we quenched it. So it's powderized here because it shattered, but basically we just dropped it in water and it solidified super quick. And so making a Prince Rupert drop, I think that the stresses that embeds in the glassy phase of this, or possibly the nanocrystalline or microcrystalline phase, this embedded stresses in the material seem to contribute to the effect, which suggests that maybe at higher pressures it will be.
Okay, and again, just for anybody watching, the LK99 is the reported room temperature superconductor. It was very big in the news a few months back, and the mainstream media has kind of cooled off on it, but you guys are kind of continuing research to see if there's truly anything there. So.
Yeah, so that's been interesting, especially because people were saying sulfur doping and phosphorus doping might do something to it, and they did. The quenching might do something to it, and it did. So based on the theory, things are checking out. We'll see where it goes from there. At the moment, these particles appear to be paramagnetic, but the one thing that's lesser known about superconducting microparticles and powder is that superconducting powders can exhibit paramagnetism under the right conditions too. So they'll get a supercurrent flowing in that, but it's a free moving powder, so it'll just rotate, and then that supercurrent causes it to act like a little magnet. So it's hard to say for sure.
Okay, here we go. Okay, so this is the working sample of LK99. You're going to give us a demo of this, right?
Yeah, so working, so this basically is as close to the original recipe that we can get, except instead of processing under vacuum, we simply used a blowtorch, and some of the particles came out looking like sand, and they don't have any weird magnetic behavior. And then a bunch of the particles came out looking black, and they do have weird magnetic behavior. The other thing we did to this sample, and you'll see that some of these particles are actually.
Yeah, they do appear to be diamagnetic, don't they?
Yeah, maybe we want some white paper for this here.
I can see them pretty good on this.
It's definitely better on white paper. Well, let me just quickly. And so these particles appear to be paramagnetic, but with superconducting particles, it can be difficult to tell. Yeah, you can see right there, quite obviously.
Yeah.
So it's, that looks like paramagnetism to me. And so basically, some of these black particles just have the right composition. So there's a specific amount of oxidation. So we prepared our sample so that half of the oxygen in the original recipe was replaced with sulfur. And so the other thing we're going to test next is having a little bit of a doping of phosphorus as well as sulfur. So, yeah. And so there's definitely a correct compositional range to get some interesting effects. Again, this is all copper and lead. There's no iron in this. So it's quite strange that it would have paramagnetism like that. One thing is if it is slightly over-oxidized or under-oxidized, maybe there's extra oxygen in the lattice, and that could be paramagnetic.
Okay.
So, but yeah, I mean, we'll play around and we'll see what we can find.
Wonderful.
I believe some folks from the University of Zurich recommended that we make a ring out of this material once it's ready. And if you can establish a supercurrent in that ring, then that ring will behave like a magnet, even though normally it's diamagnetic when the supercurrent is not flowing.
Okay.
So
that
should be a pretty good
LK99.
proof.
Yeah.
If we can get that function, if we can get that behavior out of it, that's the easiest way to prove something a superconductor or not without much doubt and without like huge equipment.
Okay.
Yeah.
Okay. So what are some of the other projects that you can walk us through? And I know that
Yeah.
we did go through these in interview format, and I may end up merging these together or do the video side by side.
Okay.
But it is wonderful to have you actually show me these.
Yeah, sure. So these, we're just soaking like gallium and indium and stuff to make chlorides of these various salts.
Okay.
And that will, this is also for LK99. We suspect that there's a recipe involving +3 oxidation states with bismuth and gallium, possibly. We will see. Basically, when we mix together the materials, it should turn into a black powder.
Okay.
And that's how we would know that there's some interesting band structure developing there. So that's actually kind of similar to what they're doing in China with LK99. So aside from that, these are an attempt to replicate Daniel Sheehan's results with epicatalytic systems. So as I mentioned, Daniel Sheehan's work is based on Vladislav Kapek's work, and basically you can, it says you can produce these non-equilibrium steady-state processes where you basically have a single heat bath,
Okay.
and then surface chemistry on two different surfaces produces an energy gradient that you can potentially harvest. So people in biology may already be familiar, but if you have something called a bipolar membrane, where that's like you have two polymers with ionic functional groups, positive functional groups or negative functional groups, then if you attach them to each other and then put that in water, the water will develop a pH gradient across the membrane.
Okay.
And in the steady state. So basically the positive and negative functional groups on the ionomer, they're like salts or acids and bases. They want to mix, but they're literally held by the polymer away from mixing. And so there's this like kind of potential energy there. And so that kind of, that biases the boundary conditions on the two surfaces of the
And so let me zoom in here really quick. So these are kind of the plastic bipolar membranes.
Yeah, so this particular device is very, very low power. We're talking nanowatts.
Yeah.
And that's being generous.
And so you assemble these.
so
you
what
assemble there are the lids, there are the membranes, and you fill them with liquid.
We
right?
soak these in water for up to a week before we even begin testing, so
Okay.
that they reach equilibrium with the water. And in fact, we soak them in water, and then we soak them in the salt solution that we're going to be using for the experiment.
Okay.
And we pre-test all of our materials. Back here you can see all of these vials are the materials we want to use in this experiment in constructing these batteries. And
okay. So
we test each of those materials, like holding it in the salt solution, and we watch for any change in pH or whatever, like conductivity of the liquid.
And there's a little counter here. Is that?
That's just for the locking cabinet.
Okay.
That's not related to this. So,
I
but
thought
yeah,
maybe that was the number and days that it had been running, but
no. So these devices, like we have a bunch of them here, and these are just a bipolar membrane around this circle, and then a pH gradient develops between the inside and the outside. And so you can take the liquid, and we have a larger one here that fits our pH probe well.
Okay.
So this is easier to read. And so you can demonstrate with these devices that a pH gradient forms, and then you can remix the same liquid from this and put it back in once it's at equilibrium, and then you can show that the pH gradient forms again after
okay.
some number of minutes or hours.
Awesome.
So there's the steady state thing, and some thermal energy is required to cause that separation. And so what we do here with these batteries is now we add a catalytic surface to these carbon fabric electrodes. And so that catalytic surface, it has different electrode potentials in the liquid on both sides due to the pH difference. And then we poke very small holes in the bipolar membrane so that there's flow back. And so those holes allow for some small electrical conductivity. And then the recombination allows some electrical current to flow off of the electrodes. It's not very efficient, the power output's very tiny, but it is a proof of concept that you can have these non-equilibrium steady states at room temperature. So Dan Sheehan proved that there was one at high temperature. I spoke about that previously. But at room temperature, it's difficult because, his big insight here was that you have boundary conditions that are different.
Okay.
My big insight with this field is that there's a minimum operating temperature to these devices, which is determined not by a heat sink, but by the chemistry involved. So you need a physical chemical process that happens in terms of milli-electron volts, roughly speaking, to have something that produces this epicatalytic effect at room temperature.
Okay.
And so you need some tail of the Boltzmann distribution to be above the energy required to get that splitting to happen.
Awesome.
Yeah.
Yeah. Oh, I was just going to ask if you were ready to go on, if you had any more projects you wanted to show us.
Oh yeah, plenty. So let's see what we got here. This is a project for WPI. So they're trying to make, that one's not fully constructed here, but this one will do. So basically, each of these devices will have a microcontroller. Actually, let's go to the other one that has the microcontroller already on there. So, and that one needs to be attached still, but you get the basic idea. So you have this linkage here, and it's based on something called a Shive wave machine, which is basically a teaching tool in colleges. And so you have a central metal rod that is soldered or welded to a bunch of metal rods that go side to side. And then when you torque that up or down, then it rotates about the axis. And due to the springiness of the central metal rod and the masses, the moment of inertia of all of the cross-laying rods, it will have a wave of torques that travels slowly through the material, and it's a good demonstrating tool for teaching how waves occur in materials. So this material, this system will allow us to demonstrate wave propagation in materials with impedance and wave speed, mu and epsilon in electromagnetism, stiffness and density in solids. But basically, you have your constituted parameters of your material that determine what your wave speed is going to be. And so here, these springs are like your capacitances in a circuit, and these weights are like your inductances. And so we're going to have 100 of these things end to end, and
they do kind of elongate and contract.
Yeah.
Right?
So this allows the moment of inertia and the angular stiffness to change with respect to time.
Okay.
Inversely under this configuration, but you can put the springs further down on this side here, and then you can have relationships between them that are not inverse.
Okay. Perfect.
So, and that allows you to have different combinations of variation in wave speed and impedance. So you can have,
this is really kind of a teaching machine then, right?
yeah. So you can have students program this. You can demonstrate various behaviors of dynamic materials, so that things that change their, or that's what Konstantin Lurie calls them. I suppose in general, you would call them parametric partial differential equations. And so parametric partial differential equations are closely related to a lot of the work that we're doing in some of our. So I haven't shown you the device yet for that stuff, but we have other devices which use parametric behavior along with nonlinear behavior to possibly extract energy from the thermal ambient energy, and that would be sort of a similar class of technologies as what Dan Sheehan's device does there, but they're active. They're not a passive device.
Awesome. Well, so far, thank you, and I know that you have more.
Yeah.
Lots and lots more stuff.
Well, let's fit in one more, and we can break up the videos if you want. So over here, this will be our test of Charles Bueller's device. So we have a diffusion pump over here, and that'll stick on top of the diffusion pump. Right now we're testing the vacuum sensor on top of it.
Yeah, so this is going to be inside of a mini vacuum chamber. Is this the vacuum chamber? It says Denton vacuum?
No. That is a sputter coater. That is
okay.
actually broken. We have to figure out what's wrong with
but
that.
we are going to draw a vacuum. Oh, and I guess the vacuum chamber will go right here then.
This is the chamber. It doesn't need to be much bigger than that.
Okay, perfect.
So just take a mason jar, run the high voltage up here, run the ground down here, and the idea is that you've got this pinwheel structure, if I can get it out of here without damaging anything. So you have a pinwheel here, you have a metal contact on the bottom to get the voltage up, and then inside there will be a pool of indium gallium, and we'll coat this this wheel here with nickel metal, and so you'll have electrical contact on the top and electrical contact on the bottom, and then you just solder on your devices. So we're taking these piezo buzzers.
Okay.
Yeah, so we have a bunch of piezo buzzers here.
You see piezo buzzers, yes.
Yeah, and so we're going to we're going to heat these up above the Curie temperature of the PZT ceramic used.
Okay.
And then we will pole them. We will apply an external electric field to these so that they have some field that's stuck in there. And then we're going to produce these additional sheets with very small posts. So you have an additional sheet on the other side with these tiny posts, and these the PCT will be here. It will have an effective negative permittivity if we have an opposite field on it.
Okay.
So it'll have some field inside of it due to its polarization, or gotta think about that again. Might not. But it's coercivity. It'll be such that it won't want to change its field in the other direction. So the effective permittivity is super low, if not negative.
Yeah. So you're basically testing just to kind of go to the most simplistic level. This is kind of a rotating Biefeld-Brown effect.
Exactly.
Asymmetrical capacitance.
Yeah. So we're not interested in measuring the exact amount of thrust that comes out of this, and also we have these newer designs where the capacitor plates will.
Okay, so piezo plates are good cap plates.
Yeah, so we'll dissolve off the silver on one side, and then we'll apply the other layer, and it'll be about double the current thickness. That's why I used 2 here to represent that. And then those just get wedged in these little things here, and that's a more finalized design here.
Okay.
So, so yeah, I mean, so if Charles Bueller's device indeed works, then if you have 4 of these in like a pinwheel arrangement, then it will it should accelerate. It should accelerate. So if you just have one device that you're testing, then it could be a capacitive interact. It could be a like an electrostatic interaction with the environment.
Well,
you can't tell for sure what that force is actually coming from. It's very like you can, even in a symmetric vacuum chamber, like if something's just very slightly off, the measured force on the thing could be much larger than the signal.
Yeah, in this case, it would begin to rotate, and there's so little drag on that because it's mounted on top of the pin.
Because of the symmetry.
Once it starts going, it should go faster and faster and faster.
Yeah, because of the symmetry, there's no one minimum energy state for that really.
Yeah.
So it should just keep rotating. It should keep accelerating if Charles Bueller's device actually produces a force.
That makes sense. And in a vacuum, the plates don't cause any resistance.
Yeah, exactly. So it doesn't matter if it wouldn't go long in air.
Yeah, that's amazing. That's amazing.
Yeah, it's a simple test, lower voltages than the T.T. Brown thing, perhaps. And I know some people say, oh, well, it won't work, but it's really, Charles says it's about the electric field. We're going to prove that out.
Yeah, no, I think that's exciting, and it's well worth visiting. So walk me through the Manelis circuit.
Yeah.
Or the Manelis device.
Yeah. So this was a project. Aidan Schaefer was working on this for a while, but the basic idea is you've got a bunch of Joule thief circuits, and then you have a magnet. And see, there's an embedded field on this magnet.
Okay.
And one of the things I was thinking is maybe the Manelis circuit's just getting power out of the magnetic field structure that's in here. Okay. Because if you don't just have like north-south in the magnet, if you have like magnetic fields that are pointed against each other, then if the magnet's not perfectly like if the magnet doesn't have infinite coercivity, which no magnet has infinite coercivity, then in principle, if you had fields that are against each other like this, then those fields want to decay into a lower energy state.
Okay.
And so if you have external fields on that magnet with these fields that are against each other.
And so the Manelis device actually sits on the magnet then, and...
What? No, so you take this magnet and you wrap it in 3 orthogonal coils.
Okay.
Yeah, and so this was claimed to output about 60 watts. Not this exact device, but like things similar to this design were claimed to output about 60 watts, and the claim was that they physically cooled down, especially like with the ferrite material cooled down. So how might that be possible? There have been a lot of physical mechanisms speculated. I think the most reasonable sounding to me is the is something called the Dickey-Maser model, DICKE, or.
So do you think that?
So it's basically the Ising model.
Okay.
So there's this thing called the Ising model, which is in general very difficult to calculate. It's the behavior of a bunch of quantum magnets arranged in a crystal structure. If you have all of these magnets, the time evolution of their orientation is determined by the Ising model. And generally speaking, you can only really compute that on supercomputers or quantum computers these days. And the Maser model is even a little bit more complicated than the Ising model. So basically, we're just going to have to test that by hand. But the idea with a Maser, with a microwave laser, is you have some medium, just like with an optical medium where you have population inversion. And with a magnet, that's super easy. So you have the magnetic field in one direction. If you flip your externally applied field very suddenly, then that magnet is in a population inverted state.
Okay.
So all of the magnetic domains are still facing this way with some delay before they decay down into the new ground state. And so what this device is doing, I think, is since you have the magnets with 45-degree angles between them, then you reduce the energy associated with each of the excited states. So instead of shifting the magnet completely upside down, you just shift it 90 degrees. Maybe you could even do 45 degrees, and then you're probably getting some sort of magnetic precession as well when you do that. And so the precession will kind of bias the way the energy goes as well, maybe. So yeah, I mean, if you have a maser with this weird design, maybe the thermal, the preferred precession direction will take the thermal noise and act as some sort of ratchet so that the precession happens in a particular direction over time.
Okay.
And so we're thinking it's some sort of maser with this sort of design to it. And that would explain potentially how it is physically cooling down. And this would be sort of like Dan Sheehan's non-equilibrium steady states, but we're actively pumping it to get that effect going. So that's my best guess at present.
Well, thank you
Yeah.
so much for sharing all of this.
And yeah, so this was Aidan Schaefer's work here. Just want to do attribution properly there, and then and yeah, it's it's a good initial attempt. And I think now that we have this idea with the maser model, we should be able to make predictions about the specific parameters that will get it to run optimally, and we can focus our efforts on those as a test of that model.
Wonderful.
Now, do you have anything else that you want to walk us through, or was that everything for today?
I mean, we have one more thing here that's actually
Okay.
this one I can kind of demonstrate. So this was our this is our apparatus. We're testing the production of bismuth magnesium composites that are similar to that alleged UFO recovered material, the bismuth
So
magnesium.
Magnesium bismuth metamaterials. Layered metamaterials, essentially.
Yeah. So I don't know where the small clamp went, but you can see videos of this on our Hackaday page, where we have the details all posted about this process. But the gist of it is you have this bismuth chloride and isopropyl. I think it's an azeotrope with water at this point, just because the isopropyl's been around for a while. And so also because when we add zeolites to absorb the water, then we don't get any reaction with the magnesium. So it suggests that water is causing some galvanic corrosion on the magnesium surface and replacing some of that surface with bismuth.
Oh, okay. So this is a chemical process rather than a vapor deposition process. I know
it's very, very straightforward.
Yeah.
So you want it to be electrochemical just because the contact at the surface can be better than with vapor dep. At least for the case of bismuth and magnesium, because they're dissimilar metals. So you want that like electrochemical processes, and then there's something called cold spray, which can get a good contact between dissimilar metals.
Oh, okay.
And so there's, but yeah, I mean, this chemical process is just galvanic corrosion. I think we're going to also probably try electroplating the bismuth onto the magnesium. I don't know about that, but I mean, we've got tons of different deep eutectic solvents and stuff to try. For this corrosion process, isopropyl just works fine. I think it cleans off the oils on the surface as well.
And again, lots of chemical vials there. And
Yeah,
so basically you're putting
this one's
layer
not.
by layer.
No, this one's not. This one's for some silver ink that we're making for.
Oh, I see. Okay.
Yeah, that one will just be for sale. It's nothing revolutionary or anything. But yeah, I mean, better silver ink for computers and 3D printing and other.
Okay, well, let me
conductive
zoom back
circuits.
in there. So then this is another project. And this is the
Yeah,
silver
yeah.
ink project. Okay.
That's true. Yeah. So this is this is a solution of silver nanoparticles in water.
Oh,
Looking like
okay.
they're more microparticles now because it's slightly cloudy at this point. But basically, we're just testing, and it's DMSO, so it might be silver sulfide nanoparticles too. So if I had a UV light, we could check it for fluorescence. But at the moment, I don't know where that thing went. So, but yeah, so just all sorts of solvents, and it's just iteration on this one. You just choose different polymer binders, and at least if you're optimizing for 3D printing, and you choose different solvents. And ideally, you can find something that forms a deep eutectic solvent with some of the silver salts.
Okay.
And so
okay.
then you can replace some of your liquid that you would otherwise, your solvent, with silver salts, which decompose into pure silver and cross-link all of your silver metal back together. One thing we were curious about doing is I don't know if we want to get into hypersonic missiles, but maybe hypersonic vehicles would be interesting. And one thing we were thinking of is you could do the same sort of process with iridium metal, and that goes up to 2,700 Celsius. So you could take like a diamond powder and have a reactive ink, is what they call it, and the reactive ink would cement all the diamonds together with iridium metal, so you'd have good electrical thermal conductivity,
okay.
as well as high temperature resistance.
So again, just to zoom back in here, just in case I confused anyone. So this is the silver ink creation system, and then this over
These
here.
are just iterations on the mixture.
Yeah, and then this over here was the layered metamaterial for propulsion.
Yeah, and I don't know where the mini clamp went.
Okay.
I think River put it somewhere, but I mean, yeah, you can just go to the Hackaday page, and you can see as we just clamp them together, we blowtorch it for a while, and it cements them together. We found actually what's interesting about this is that basically we were trying to find optimal process conditions, which we'll post about on Hackaday soon,
Okay.
hopefully. And we found actually that the initial process that we tried was pretty much optimal in atmosphere. But actually, if you process it in vacuum, it actually starts working a lot better.
Oh.
So
okay.
that was exciting to find. So that suggests that it has to be processed in vacuum to be optimal. So that is really weird. If you want to make it this way, like there were some claims that maybe it's a metallurgical process, and if you have some small amount of bismuth dissolved in magnesium, then as the temperature decreases, basically when you have metal impurities, they tend to go to the grain boundaries.
Okay.
But there was some claim maybe that the bismuth metal goes to the actual surface of the magnesium when it unmixes. And so maybe if you dissolve, that's one thing we can test, I suppose, under vacuum is, that would still require vacuum perhaps.
Yeah.
Or at least a molten salt bath. But you could take magnesium, try to dissolve some bismuth in it, and then cool it down and see if the bismuth comes out on the surface. Because then that piece of material, it could just be from magnesium refining. You could just have some crucible that they were using to produce magnesium, and over successive meltings, you would get this layered structure on the edge of the crucible where it's colder anyway.
Wonderful.
So that's the thought.
Well, Michael, thank you so much for walking me through all these projects. It's really exciting. It's exciting to visit your lab. It's exciting to see everything that you guys are working on. It's exciting to be here in Worcester, Massachusetts, and I'm just looking forward to more good things.
Cool. Yeah, hopefully we can figure some of this stuff out.